Thank you guys. It's a huge honor to be here. It's been a long time since I've been at an academic conference in a speaking role, and the papers really inspired me. I'm excited to talk with everyone after. I've got 15 minutes, so I'd better jump into it. So I'm here to share some techniques that we use at realtor.com in terms of sort of combining session-based and feature-based recommendation and applying some techniques like transfer learning. Along the way, we're going to walk through some interesting kind of techniques that we use for dealing with structured data in a deep learning setting. So the outline of the talk is I'll look at the specifics of the recommendation problem we have at Realtor and kind of walk you through what we do at realtor.com. We'll look at our architecture in terms of how we combine session and feature-based recommendation. And then those tips and tricks I talked about. I'll talk about some techniques for transfer learning for recommendations. So you know, there's a lot of transfer learning that goes on in images. There's some transfer learning now happening in NLP. The same techniques can apply to this context. And then I'll talk a little bit about how we scale our model into production. So realtor.com, we call ourselves, or we like to think of ourselves as the home of home search. So users come to the site. We get about 60 million monthly active users. They're looking for their dream home, predominantly US-based. We get about 260 million searches a day. That translates into over 1 billion user item interactions, like distinct users to distinct item interactions. The data is a little bit interesting in the sense that we don't create the data around the listings. We're collecting that data from MLSs across the US, as well as individual brokers. So the data has a bunch of variance to it. We have to do a lot of cleaning of the data, sort of converging the data into our own sources. And even after we do that, we have to be really careful about biases introduced by the fact that fields are filled in certain MLSs and not others, or by certain agents and not others. So there's some interesting problems there. We have an inventory of about 10 million homes, and a lot of user interactions captured across the apps and the website. We combine those into a recommendation system. Predominantly on the search ranking side of things. Just to give you a flavor of the data that we're dealing with. So, we're looking at listing data. These are things like categorical variables like, 3 bedroom, 2 bathroom, categorical like a townhome, a continuous variable like, 2,431 square feet, images and text. And so, we'll cover each of these a little bit, but mostly I'm going to focus on the structured data side of things because it seems to be sort of a little less well known. A lot of people know how to embed images or text. In terms of the recommendation problem at Realtor, what we have is a series of very unique products. So this isn't like a movie that millions of people have seen. This is a house that can be sold once. It has very unique features. It's likely, unless it's built in a particular way, very different from every other house. And so, in that context, every home is different, and helping people find that perfect home for them is a real challenge. Freshness is super important. So, we're dealing with markets where sometimes listings will sell in days. So, a house will go up on the market. Even before it gets to our website, real estate agents can be shopping a house around. So, we really need to be providing users with the most fresh listings, and that availability can change quite regularly. And so what we want to make sure of is that the listings on our site are as fresh as possible, that all of our recommendations, that all of our searches are providing recent listings. As you can imagine, there's heavy geographic influences. So if I come to you and I say, hey, I've got the perfect house for you, but it's nowhere near where you currently live, it's nowhere near your job, it's nowhere near your reality, then it's a useless recommendation. So these geographic constraints and the uniqueness lead to a lot of sparsity in our problem space. And the other thing that's kind of interesting is because users are making the biggest financial decision of their lives in most cases, they're exploring the space in a way that sort of is slow and somewhat methodical, and they're beginning to go on a journey in terms of market understanding, and that often changes their preferences. So they may come on starting with I really want a 3-bedroom, 2-bathroom apartment in downtown, and by the time they're actually looking at that sort of price range and comparing that to townhomes in the area, and then maybe they've met a partner in the meantime, like time frames can be months or years. We see a change in the preferences of the users over the course of their journey. So we predominantly work within the search framework. So we're sort of re-ranking the search results and trying to present the best users or best listings to the users at the top. We use deep learning models based off of PyTorch and the FastAI framework. I can't recommend that framework enough. It's amazing. There's a new cohort starting up in the fall. So if what I'm saying speaks to you, or if what I'm saying is completely not understandable, look that one link up. That'll be the one thing you take away from this talk. It'll be worth your while. We do feature-based listing representations. So, I talked about the listings being unique. The interactions are very sparse. So we try and represent our listings in terms of the features and then combine those features into an embedding. And I'll walk you through how we do that. We have sort of users are represented as that sequence of listings as they come in. So the interactions that a user's having with listings becomes the representation for that user. And there's a variety of ways that you can combine those, and I'll cover that very briefly. I'll talk a little bit about transfer learning of listing features as we go and how we modularize our architecture for production. So this is the abstract architecture. I think it's, it should be familiar to most people in the context of a recommender system. We take our listings and we embed them into a latent space. We combine those latent space representations into a representation of the user based on the sequence. And then taking that user representation and a sequence of listing representations, we combine those in order to predict the interest on those. And you'll see why I've separated it when we get to the production side of things. But I like to think of these sort of three main tasks in the context of recommendation. So this is the part where I'm going to dive pretty deep into some deep learning techniques, and hopefully people can follow along. A lot of the data we deal with is this structured listing data. There's a huge range of it, a lot of categorical variables, really high cardinality categorical variables like the city, the state, things like that. And so embedding those is a really challenging task, and we've got some things that we've used. I found this technique of using denoising autoencoders through this Puerto Segurno safe driver competition, Kaggle competition. Denoising autoencoders, or autoencoders in general, they're just a network that basically takes as input a set of data, tries to embed that data into a latent space that allows you to reconstruct that same data. So you measure the autoencoder on the loss in terms of its ability to reconstruct its input. A lot of autoencoders, they'll have a sort of a compression in the middle of it where they shrink the latent space down to a small bottleneck. In this case, we're using swap noise or denoising autoencoders. So instead of shrinking the latent space down, what we do is at the input side of things, we randomly vary one of the input variables with a sort of basically a 15% chance that any variable is going to be randomly swapped with one of its neighboring values. And so you end up with this value that's coming from the distribution of data, and that works out quite well in that context. Each of these other techniques I'm going to cover in detail, so we'll just step right into it in the interest of time. So for categorical variables, when you one-hot encode a categorical variable, feeding that directly into the fully connected layers is sort of a very common technique, but it turns out that if you treat each categorical as its own kind of embedding space and you one-hot encode them and then feed them into an embedding of sort of a size max cardinality over 2 and 50. We find 50 seems to be about the biggest. This is a technique I kind of pulled from FastAI, and it's a very useful one for embedding kind of the listings. The embedding is what feeds into the fully connected layer. And we find that this really improves the sort of categorical representation, particularly in downstream tasks. So it's quite a useful technique. The second is more on the continuous side of things. So the Puerto Segurno competition, the person who won it used a technique called Gauss rank, where essentially what you do is you take the data that you have and you rank it based on the values, and then you remap those values into a Gaussian distribution of zero mean unit standard deviation. It turns out neural nets really like this kind of data. Transforming the data in this way, we've seen a 4 to 6% improvement in downstream tasks, depending. I'm sure you're going to see, depending on the task, big, like significant differences. But it's a really valuable thing. I can't get into too much detail in terms of the functionality of it, but if you just Google the term, you'll find the techniques there. Definitely worth looking up if you deal with continuous variables. And in particular, if you deal with them in terms of like trying to predict the rank at the end of the day. So we do all our normalization using Gauss rank. People using sort of standard fixed learning rates or stepwise learning rates, there's a lot of developments that have happened in terms of learning rate, like cyclic learning rates, stochastic gradient descent with restarts, and one cycle. All of these techniques I've picked up from FastAI. If you Google the terms, you'll find a lot of information on them. If you're training your model currently on fixed learning rates or stepwise learning rates, plug this technique in and I guarantee you'll see a significant improvement in performance. It's that straightforward and it's that powerful. Our contribution to this, so previously we've just been taking the Puerto, Segurno and the FastAI techniques and sort of throwing them together. And what we did when we analyzed the problem, this autoencoder is taking categorical data and continuous data and feeding it through to produce categorical and continuous. Typically with an autoencoder of this type, you're sort of measuring it on mean square error loss. So mean square error loss doesn't really make sense in this context if you think about what the data is that's coming out the other end, right? You're dealing with one-hot encoded categorical values with super high cardinality, potentially, versus continuous variables. So you end up with sort of massively outweighing the continuous variables by the continuous variables by the categoricals. And there's this sort of funny imbalance that happens. Instead, we use this weighted combination of sort of mean cross entropy per categorical and mean average error for continuous, and we find that that has a huge impact on the ability of the network to kind of learn the latent representation in a way that reduces the loss. So this is our own technique. We're working right now on an ablation study that covers this and all the other techniques, but basically what I've given you is the sort of our best findings so far. So this is a really powerful technique in terms of embedding categorical and continuous data. I mentioned, representing the user. I don't have time to dive into the different techniques. We've used a variety of different things. Incremental weighted averaging is sort of the easiest learned weights, but it allows us to work in real time for all user interaction data. We used AWD-LSTMs in sort of like a training and a research environment, but what we found was, for the 60 million users, the billion interactions, it was too hard to keep that up to date in real time, kind of feeding that through. We're still working on kind of using in-memory databases to make that happen, but it doesn't seem to be working at this stage. In that light, we're exploring CNN models. They're obviously faster. We're super excited about the idea of attentional models, but what we're finding is that the user states can kind of lag, and you'll see what I mean by that in the context of the system that we've developed. And we want to front load as much computation as we can. So I'll talk about that in the next few slides. We'll get into kind of how I modularized the system. What we're predicting on is essentially, we started with normalized click-through rates, so we used that Gauss rank function to kind of set up a range of click-through rates. What we found is that based on the sort of the usability of our site, there's ways for users to just literally click through listings so they can go next, 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 next. That's not a good, strong signal of a user's intent or interest in the listing. So we use this normalized dwell time. It seems to work reasonably well. And what we've been using recently is a sort of a difference in dwell time. So we feed 2 listings through the model, and we train it on the difference between the dwell times, and that allows for a more continuous representation. And we're actually working on sort of evolutions of that. Our architecture is modular in the sense that we try and treat sort of listing representations, user representations, and the time on listing inference API independently. And what I mean by that sort of in terms of production we'll get into, but I did want to touch briefly on the idea of transfer learning. So when I have this autoencoder embedding, basically the middle of the autoencoder is the point where I have that rich embedding that I'm using to represent my listings. What we do is not sort of run our data through it and take that embedding out and feed that into the next model as an input piece. We actually take this part of the architecture, copy this head of the architecture into the new system and train end to end. Now, in order to do that, you have to do traditional transfer learning techniques like freeze that part of the model, train the rest of the model until it catches up, and then slowly sort of unfreeze those layers with a kind of a weighted representation in that context. But we find that works really well. In terms of production, we've got a system basically where there's new listings coming in, there's user interactions coming in, and there's these re-rank requests coming in from our system. And we're trying to deal with each of these in parallel. And so we've broken these up into independent systems. So we have sort of an embedding system that its whole job is to take in new listings or listing updates, generate those embedding, those listing representations, and through a kind of a pub sub or a replication model, get that data to the model serving or the model inference machines. Similarly for users, they're actually one of the subscribers of that system, and they're sort of taking the sequence of user representations and feeding that through. And then the prediction goes into that sort of, or takes that same context or that same approach. So we've got these in-memory databases, and the data gets transferred across to them. My time's up. I'll just dive briefly into the future work. So, we want to explore user representations in production. There's a bunch of different things. We're looking at this paper called Mix-Up, which uses a weighted combination. Swap noise is really interesting on the autoencoder side of things, but we actually want to try it on the interaction side of things as well. And vectors and latent spaces are super interesting, so using them downstream is something that we're beginning to explore from a data science usability perspective. So thank you so much for your time. Please reach out to me if you're interested in deep learning-based recommender systems, and I'm happy to take a few small questions because I think I've gone a little over.
Thanks so much for the talk. It's very interesting. I have two questions. The first one is, here. Yeah. When you get this user representation, do you learn user embedding separately, or this user embedding is kind of aggregation of your atom embedding? First question.
Yeah, so the user embeddings are sort of taken from the listing embeddings. They're learned from that sequence of listing embeddings.
Okay, so kind of you use kind of RNN.
Yeah, so we've tried different approaches. We've used just a weighted average as the simplest model. You can use RNNs, like the model we've explored is the AWD-LSTM. It's commonly used in language modeling. And then we're looking at CNN-based models and attentional models as well.
Okay, very good. The second question is when you, I think since each day you have so many new homes, and then you have to come up with candidate generation. Candidate homes. So do you optimize that part to use your learning?
Yeah, it's a good question. So we don't optimize the upstream side yet. We're just sort of, it's a very traditional database. It's just pulling a wide range of samples, and then we're optimizing sort of the re-rank side of it. But we do want to explore that side as well, for sure.
Cool, thank you.
Hello, really nice talk. I find it really fascinating that you're building your whole infrastructure on PyTorch and fast AI. And I think it's something that a lot of startups are trying to do. So my question is, now with PyTorch 1.0, it's a little bit different, but how are you solving the model serving side? Are you using Onyx? Are you embedding the Python code? What are you doing there?
Yeah, so there's some work done to sort of do conversions to Caffe. We've tried it in production in a variety of ways. In the past, we've even rewritten it in TensorFlow in order to get the sort of the benefits of TensorFlow serving. Super excited by yesterday's announcement of PyTorch 1.0 and the Onyx side of things, and we're looking at sort of that as our flow going forward.
Okay, but now in production, you're using a combination of rewriting and getting stuff done however you can. The model inference side of it is actually not so bad. So we've managed to get away with sort of pure PyTorch models on the user, like on the latent representation side of things. The autoencoders, the speed of them is fast enough. On the listing generation side of, on the user representation side of things, that's where, like I said, the AWD-LSTM doesn't kind of meet the needs, and we're hoping that maybe by going to the more optimized models, like Onyx, and going to kind of in-memory databases, we
we could probably run those models at some point.
Okay.
But right now, it's more of a very simple kind of learned weights in the, like during training, we learn the weights, and then at inference time, it's just this sort of weighted incremental kind of system.
Okay, thank you.
Yeah.
Hi. I have a quick question. I just want to see how do you model exactly the time and freshness of the listings?
Yeah, so we have that as an explicit kind of input variable into the system. So when we're dealing with our training data, the model is aware of how old the listing is, and so it's able to model, not just the age of the listing, but also the user's kind of relative preference to listing age.
And the model is LSTM right now, or is CNN?
So it's a feature that we feed into the model in terms of the sort of like we're capturing it on that side of things. It's a sequence-based representation. So we do, like when we represent the user, we've explored a number of things, but the current is just like a weighted decay kind of representation of the user embeddings. Or sorry, the listing embeddings. Yeah.
Okay, thank you.
Excellent. Thank you.
Thanks.